Okay, so we would like to compute the triple integral of z over the domain u, where u is the upper half of the ball of radius 3 centered at 0. We're going to use spherical coordinates to that end. And let's begin by describing u in terms of those spherical coordinates. So the spherical coordinates are rho, theta, and phi. And rho is going to be between 0 and 3. Theta, let's think about it. We have the upper half of a ball that projects to a full disk on the plane, and that means that theta goes all around, so from 0 to 2 pi. And here some people might say, well, why don't you put strictly less than 2 pi? Because the angle theta, when it's 0, it's the same thing as if we take it to be 2 pi. These are the same points that it describes. But we're talking about something that has no contribution to the volume, which means that it's not a problem to put less than or equal to, and it doesn't change anything. It makes things visually a little more pleasant, in fact. Anyhow, let's also talk about phi, since we're talking about the upper half. That means that phi is going to be between 0 and pi over 2. And, you know, again, sometimes we need something a little more tangible to understand the range of the angles. And what I suggest is that you take your region and you project it, let's say, on the XY plane. If you project the ball or the upper half of it on the XY plane, what are you going to get? As I said before, the full disk of radius 3. And here is where you can see that the angle theta is going all around. So it starts here at 0, it goes to pi over 2, pi, 3 pi over 2, come back to pi. And if you do the YZ plane, then the upper half of the ball is like this. And again, you can easily see what happens with phi. So phi is 0 on the positive z-axis, and as you move in either direction, it reaches just pi over 2, right here and here. Okay. That is what justifies this range. Now we can proceed with the computation. So let's arrange the endpoints, the limits of integration. So 0 to 3. Let's match that with 0. 0 to 2 pi. We match that with d theta. And 0 to pi over 2. We match that with d phi. What is z? Z is rho cosine phi, right? And what is the Jacobian? Rho square sine phi. Okay, so let's do our integration. So the first integration is with respect to rho. We have rho cubed. The antiderivative is rho to the 4 over 4. Cosine phi, sine phi, and we want to go from rho equals 0 to rho equals 3. So then we have 0 to 2 pi, d theta, and 0 to pi over 2 d phi. So when you plug in 3, you will get 81 over 4. You can pull that constant out of the integral to make your life easier. And then you need to integrate with respect to theta. But there's no explicit mention of theta, which means that everything is constant here. And since it's constant, we can do cosine phi, sine phi, times theta for theta equals 0 to theta equals 2 pi. And this is d phi. And of course, from this, we're going to get a factor of 2 pi. We put this outside, so that will give us 81 pi over 2. We did a cancellation between the 2's. And finally, we have this integral, which is a classical integral to be computed with a substitution. What substitution would that be? U is equal to sine phi. Du is cosine phi d phi. And remember that when we apply such substitution, we also, we also replace the limits of integration by the corresponding values that we obtain from that substitution, meaning we take 0, we plug it into sine phi, and that gives us also 0 because sine of 0 is 0. We take pi over 2, we plug it into sine phi, that gives us 1 because sine of pi over 2 is 1. And this becomes u du, which gives us 81 pi over 2 times u squared over 2 from 0 to 1. That's another 1/2. It makes the whole thing 81 pi over 4. And that's it. Thanks for watching.